Hope everybody is enjoying things so far. It's my pleasure to introduce Mats Öberg this morning. Mats was the, I'm going to say, the senior PhD student in Paul Siegel's lab when I joined back in 1997. And so many things I learned about coding, I learned directly from Mats on the whiteboard, which was very nice. And those of you who weren't around at that time, it was actually a very exciting time because turbo codes were being put into real things. And I know at the time, I was under the impression that Marvell hired you so that you could help them put turbo codes into magnetic recording. I don't know how that played out exactly. But yeah, so I think I'm very excited to get some industrial perspective on what's been going on there for the last 20 years.
Yeah, thanks, Henry, for the introduction. Yeah, actually, we had a lot of great times at the whiteboard in that lab. And it was usually, I came up with some crazy ideas and he made me land. But we had a lot of fun. So, okay, I'm going to talk about some air control coding for data storage. It'll be very light on theory. And I also will try to avoid machine learning and artificial intelligence today. So a little note from our lawyers. That's the industry. So it's pretty clear to everyone in the industry that SSDs outperform HDDs in pretty much every metric. They're orders of magnitude faster. The access time on HDDs maybe 4 milliseconds for a drive to spin and 50 microseconds for SSD. I don't think any one of you really have an HDD in your laptop. So it seems like HDDs may not be all that interesting. The cost difference is maybe what keeps HDDs interesting. It's the raw storage is maybe 6 to 9x, maybe coming down a little bit more, but with the total cost of ownership, it's maybe more like 3x. So, well, what about HDDs? What percent of data in the data centers are stored on HDDs? Do we have any guesses? It's about 90%. It will slowly go down, but it'll take so long time because data is growing so fast. So even just to build fabs to supply will take a long time. Anyway, I want to go back to figure 1 in your communication systems textbook and kind of view the storage system from there. We have a source, that's our user data to be stored. We encode it, we transmit the data, we write it to the media in some way, and of course, storage media. And then we note that the communication here is communicating with the future. We're storing data, it's not point A to point B like a wireline. Then when we want to read the data tomorrow or 10 years from now, we read it, go to receiver, and decode it. And then the sync is recovered data. One thing that makes SSD and HD actually quite interesting from storage people is that you can do this proprietary. You don't need to have interoperation with anyone else. You just write your data and you read it back. If you want to come up with some weird scheme, you're free to do that. So it actually opens up for quite a bit of innovation. So now we're kind of expanding this diagram a little bit. It looks maybe a little overwhelming now, but we just start. We have here the host, kind of, there's the source, and as we know, it's also the sink. It puts data into the memory, DDR. Run length limited encoding, potentially some maximum transition run encoding, and typically today mainly LDPC encoding. The data to be written is sent to a preamplifier that kind of puts a write current to write head that excites the media, kind of magnetized magnetic grains up or down. And I'll come back a little bit more to the magnetics, the grains about that. And then it's kind of on a read-write arm, the read-write head. Then when we read back, we seek the location and the read head. The preamplifier once amplifies the very small signals, send it through an analog front end with some preconditioning, some high-pass filtering, a variable gain amplifier, continuous time filter, before we sample it with an A to D converter to get digital information. And here I show kind of an impulse response that goes from write data to the output of the ADC. This one is short, it's only about seven taps. In reality, it's much longer. And how do we build an trellis-based decoder for a very long impulse response? Well, we add a lot of states, so that's not very practical. So we do a partial response equalization. So data storage HDD was kind of pioneering the partial response maximum likelihood. Now we're doing this with a soft output Viterbi or a BCJR. I use the term SOVA, interchangeable with that. And then we have an LDPC decoder, and we do the turbo iteration between these two. And then finally we get the data, RLL decoding, and we keep going there. I'll not talk more about modulation coding. It actually used to be a very hot topic some 20 years ago. And it's actually still very interesting. We still think there's things to find there, but I will not talk more about that today. Okay, so HDD, it's a spinning media. So you basically have to seek to the track you want to read, and then you have to wait, well, almost sometimes up to full revolution. And that means you have about, one revolution is about 8 milliseconds for a 7200 RPM drive. So it's about expected time 4 milliseconds. And of course, the media speed is your data rate. We're never really going to go beyond 5 gigabit per second or so. And that also limits the throughput. I said latency does not really matter, and IO operations per second doesn't really matter. Of course it does, but compared to SSDs, they're orders of magnitude faster. If it really matters, you go with an SSD. So some of the kind of noise and defect sources, of course, we always have electronic noise. We can't really get rid of that. But with granular media, it's basically small magnetic grains that you magnetize to point up or point down. They're really poorly defined bit edges. So if you kind of see this kind of a model of media, and we write 110011, so 2T pattern on the bottom track, 3T on the next track, 4T, and then random data. You can see it's not very well defined, and this kind of some of the sources. Another is, we show here up on the left, is squeeze when you write the neighboring track. So because it's data center, it's a mechanical system, and you may get some vibrations going on in the data center. There's fans, there's other drives that are doing seeks. So you may see some vibrations that may actually push your write head off track when you write, and of course also when you read. But in particular, when you write, you interfere on the neighboring track, and that's a very big source of error. And you may sometimes need to have additional margin between the tracks. We have, of course, adjacent track interference is basically you keep writing the neighboring track multiple times. Well, the stray fields may eventually flip some grains on you. So sometimes you need to go in and refresh the track. Okay, so let's move on to the turbo equalization, the coding. So I mentioned we did this partial response equalization here, and then we take that output, non-linear. We use non-linear soft output Viterbi detectors, and that generates LLRs, or effective probabilities, that are then used by the LDPC decoder, and then we feed back and iterate. And depending how many iterations, but obviously if we want to do 4 iterations per code word, well, it needs to operate at 4x the rate, the code word rate that's coming in. There are complexity and performance trade-offs. We know a short LDPC code, shorter than 10,000 bits at the high data rate, is not very efficient. We have a sweet spot of approximately 90% data rate. Much higher, you can't fix defects, and much lower, you have too few grains per bit, and number of grains per bit is efficiently or SNR. So it turns out 90% is about the sweet spot. And we see you grow up to about 2 kilobyte code word size. That's kind of where the gains start to disappear. Of course, there's some additional gains. But then you go into complexity issue. But 2 or 4 kilobyte, and note the user size is 4 kilobytes. So that's the reason for using 4 kilobyte size. And no, you're right. So we use, in many cases, the industry uses a kind of shared decoder. So when one code word is decoded with a SOVA, the LDPC would be idle, so you can actually run another code word in the LDPC decoder, and then you switch. And as soon as one code word converges, the next SOVA slot is used by a new code word. So that's pretty straightforward. You can use to speed up. You can use, parallel SOVAs. So you do small chunks of the code words. That's more of a kind of complexity trade-off. Do you want to run it very fast, 4x code rate, or do you want to split it up into 4 chunks and run at the kind of normal data rate? So
how does the latency with that compare? Like if your seek time is most of the latency, how do the latencies here compare to like the seek times?
So basically you need to process more or less a code word per code word that's coming in, otherwise you'll build up. So it's pretty quick. We basically, a couple of iterations, I don't know, we run 3 or 4 iterations per code word time. And you don't want to run too many more iterations, because then you also, that's another thing I didn't mention, is the power. We could add more area and run 20 iterations per code word, but we would burn, first of all, more chip area, which is a cost, but it's also power is a significant cost. And the LDPC decoder is, apart from the spindle spinning the media, the LDPC decoder is a big power hawk on the systems, or the Iterative decoder. Okay, so I talked about write squeeze, how kind of when you write the neighboring track, it drifts over. It's a little bit driving down the freeway. A drunk driver veers over into your lane. He may hit you a little bit, some damage, or he may drive you off the road. Always driving off the road is not what we want, but that's basically code word failure in this case. So if we have a significant squeeze, we'll fail the code words. And one way to deal with this is what we call long sector format, or interleaved sectors. So assume you have a number of sectors like this. You split them up into chunks, and then these chunks, when you write them to the media, you interleave them. So basically you see kind of, well, it's hard to say exact, but trust me, this red piece occurs here after every kind of checkered piece, which is kind of an intersector gap. It can be a servo wedge or just an intersector gap. And this is rather effective, because now and then you deinterleave when you read. And let's see what happens when you have a big squeeze. So let's go back without an L sector. We have a severe squeeze. Let's say we fail. If this happens, we fail 2 code words. Now with L sector, well, the same squeeze, but as we deinterleave, we see kind of this degradation spreads over multiple code words. This is a very, very efficient way of dealing with squeezes. But there is, of course, a problem, is that if you want to rewrite just one single user sector, and you may not think that's common, because if you look at the file sizes on your computers, it looks like you have multiple 4K sectors. But in the data centers, there's a lot of times to just write one for a database. They update one thing. And that's a little bit of a problem. So if you want to rewrite the sector, you have to read the whole L sector and then put in the new one you want to write, and then rewrite again. So it's basically write operation now becomes a read operation followed by a write operation. So you basically have 2 revolutions here. And the performance is significantly degraded for this. And one thing also, if you now go to the 4K, 4K times 60, why not go to bigger code word size? Why not do a 64K code? Well, the complexity, it's a lot of area to do a full 64K code. And the benefit is questionable. But not saying that that won't happen. I mean, we're constantly reevaluating things like this. But there is actually in something called shingle magnetic recording, which is quite common these days. It's getting more and more common. The data centers were a little hesitant about it in the beginning, but now their software stack starts to be prepared for it. And let me tell you what that is. So first start with what we call conventional magnetic recording. You basically write the track, and we see here we kind of have the writer here, and the media slides under this, and we write this data. And the track pitch is basically limited, or the track width is limited by the write head width. You can't write narrower than your actual write head. That's physically impossible. But with shingle recording, it's like shingles on a roof. You write them subsequently. Each track overwrites piece of the previous track. But then, of course, you need to write one track at a time. And you see this kind of the newly written track is fairly wide. And we can get basically as narrow track as we want to. And of course, SNR plays a role here. We can make them very narrow, but we won't be able to ever read them back. And of course, read, modify, write, yeah, forget about it. You have to write at a different location if you want to rewrite the sector. And then as you have enough kind of sectors in the shingle zone that's been kind of replaced somewhere else, you need to do, for SSD, we call it garbage collection. You read it and you move all the data and you free up this zone. But this is obviously a perfect fit for the long sector format. Another thing also being quite common, because you have this shingle recordings, you still have to rewrite everything if you rewrite the track. Well, it's called track ECC, and it's basically an old-fashioned product code. So you take the LDPC codes as you write them, code word 1, 2, 3, and you XOR them all into parity sector. And then at the end, you write the parity sector. And obviously, if you fail any one sector on this, you just read all the other sectors and XOR them, and you have that sector recovered. That's quite simple. And you can do this with shingle magnetic recording with really no penalty. I mean, of course, there's a small code rate penalty. So out of 400 tracks, you write one parity, comes out to about 0.25%. And so this is very interesting. But okay, what if you fail two sectors? Well, you could do some kind of Reed-Solomon code. That's fairly straightforward. But that's always with hard decoding. And if you want to correct many sectors, you basically need many parity sectors to do hard recovery on more than one sectors. But there is a solution which is actually soft track ECC. If more than one sector is failed, so for example, we note that we XOR all the sectors, including the parity sectors. For some reason, that should come out to 0. I guess that's from the design of the parity sector. But assume now that we fail 3 sectors, and I just call them I, J, and K. I picked some random locations here. Now, when we decode, okay, we failed to converge this sector. We store the kind of FIR memories. We save them for later. And then we XOR all the other converged sectors. And we just call that P prime. Or you can call it something else, but call it P prime as XOR of all converged sectors. And that is also what we call a track ECC syndrome. And if I done the math right, if we take the failed sectors, well, their XOR should equal P prime. So then what you do is you do an iterative decoding on this. So the upper part of this figure, you clearly see, I mean, it's the same thing. We do the turbo iterations. So we take the first code word, we do the turbo iterations. Then we take the output probability and send them to track ECC decoder. And now, effectively, this track ECC decoder, it's a RAID 3/4 code in the product code, because everything else is corrected. And since most, I mean, even if you squeeze, but most reasons you fail is that you barely failed. Right? So you have a lot of code words that are almost taking converged. You need a little additional boost. So we have seen that you can correct, I mean, up to about 10% of sectors on a track. We have 400 sectors on a track. We may have, at about 40 failed sectors, we see that they start to fail. Of course, it all depends on that.
Are the errors typically bursty, or are they more or less independent?
They're typically bursty, that it's kind of one, kind of what I showed with squeeze. It's kind of you squeeze the neighboring track, or you read off track. And that's maybe these kind of vibrations. They may be fast, but we need to realize that we have, I mean, on the order of, if we just stay on a track, we have on the order of 60,000 sectors per second. And so vibrations in even 10 kilohertz still is, if you're off track, it still impacts more than one sector. So they really burst in that sense. But of course, there's also random errors.
Are you guys able to detect when you're off track a little bit and adjust the LORs? Do you realize, oh, that the reason these are bad is because we're off, and so those LORs are unreliable?
And yeah, there are ways to do that. That's it's not necessarily looking that you're off track, but you can look at basically the LORs also.
It's a bursty check.
Yeah. Yeah. So this is very good, but of course, and you only need to read the whole track if you fail. So if you just want to read a couple of sectors and they decode perfectly fine, yeah, you're done. You seek on. But of course, if you fail, you need to read the rest of the track, which has some. And of course, this can be extended to, I mean, what we call zone track ECC, where we pair it to get another dimension. For example, we take multiple tracks, we do kind of multiple logical tracks. So we have, instead of having for a whole track, we do it on sub tracks, and we add additional parity. But of course, this basically requires single magnetic recording. There are some drives with conventional magnetic recording that uses some kind of track ECC, but it's very costly in terms of how they need to deal with this. Okay, so this kind of the first part I said on the HDD. So just talk about it from a communication system point of view. I think I gave you what I would say a rather brief overview of magnetic recording. We talked about this turbo detection and how we can handle in particular the right squeeze. That's the main thing, how signal recording looks like, and then the soft track ECC. So now we want to move over to SSDs. So what is the approximate read latency of SSDs? Can we get some answers here? I was not clear when I mentioned 50 microseconds. So it's, the right answer is C. That's how I see who's paying attention. So I'll give a little bit kind of a similar brief overview of NAND flash and really focus on coding perspective. I mean, there's so many things that can be done there. And some of the impairments, it causes errors. And then focus a little bit more, but not too much, on LDPCs for SSDs, and talk a little bit about hard and soft decoding, read, retry, RAID. Do a little diverge, hopefully, into trellis coded modulation. Just has some interesting aspects there. So in the beginning, and the beginning was 1987, when NAND flash was invented, they used what they called single level cell. Basically, you write data, you store a certain amount of charge in a NAND flash cell. And of course, the charges have some kind of distribution. So you basically don't write anything. 0, you write in a charge. And I think this graph is a little bit optimistic. It seems like you would never make a single bit error if you tried to distinguish between these two. But on the other hand, you see why we may have multi-level cell. So you can store 2 bits per cell. So by just doing some improvements, you can get 2 bits per cell. And now most drives, particularly high-performing drives today, are actually TLC, triple level cell. But what do you see? When you go from 1 to 2, yeah, you double your capacity. When you go from 2 to 3, you get 50%. But you also you double the number of levels. So when you go to QLC, you have 16 levels, but you only get 33% more capacity. And PLC gets 25 more compared to QLC, and you have 32 different levels. Of course, more errors, which problems. So QLC is, I mean, it's happening. It's the big market for QLC now. And a few years ago, everybody doubted, will that ever take off? So I guess I will say PLC will take off based on history. But let's, for simplicity, I don't want to have too complicated graphs, so let's go back to MLC just to, so what you do is you compare the read voltage with the reference voltage. So you basically set the read voltage and tell what side you're on. For MLC, if you look at the lower bit, sometimes it's also called LSB or MSB, but there is really no difference in significance on the bits itself. So I try to use lower bit, but forgive me if I use LSB also. But you only need one reference here. But for this, you need 2 references. So typically, the upper bits typically have a slightly higher error rate. And see some of that. And this typical hard decision is used for decoding. And why is that? Well, to do soft decision, you really have to do multiple reads. So each read requires kind of one more level. So it's basically to do a soft decision where you do just 3 reads, and then you get 2 bits soft decision. It takes almost 3 times as long to do. There are some things that the NAND can do to shorten it a little bit, but it's significantly longer time to read. So, and this adds latency to the throughput of the performance. So because of that, we want to do kind of the hard decision decoding is preferable. And I mentioned that TLC dominates today and QLC is growing, and I kind of want to point out here that we're doing kind of gray coding. So when you flip between 2 levels, you only have 1 bit that changes. That's the typical way it's done. And there are different forms of this gray coding that, depending on the NAND vendor, can be different. And so it's basically, we have this erase state, which is basically you erase the media and it kind of comes to this state. And then when you write, you kind of add charge to it. So let's take a bit of what's happening. What's the problem with NAND? Well, there's really three different significant error sources. One is endurance, and that is when you write the media, you cannot kind of overwrite existing data. Before you write new data on a piece of media, you have to erase what you have. So that's what we call program erase cycles. So you write the media and you use it until you're kind of happy or you have replaced enough of the sectors somewhere else. And then you erase it before you use it again. And these kind of program erase cycles, 1 to 10K, maybe SLC can be even more. TLC, 3,000 to 3,500 seems to be where most are today. And QLC, some numbers were below 1,000. Now they seem to push it up above 1,000. But as you see, if you look here kind of between P4 and P5 here, you see that the red, which is 3000 P cycles, kind of the distribution widens. So you get more bit errors. Retention is basically you write the data, and after a day, you have the blue curve, which is 1 day retention. You lose a little bit of charge, or the charge changes. After a year, it's even more. And if you see here between P6 and P7, which is you really see the red and black, which is 1 month and 1 year, the error rates start to creep up. And there's something to think about if you have a NAND that's just sitting there and not being plugged in. I wouldn't trust that too long. I mean, probably at least once a year. Plug it in and read some data from it. And then read disturb. When you read neighboring word lines, neighboring cells, you change the charge. Oh, well, when you read something, you change charge of the neighboring cells. So 100,000 read disturbs, you start to see some issues, and this is something we just have to keep track of inside the drives. And of course, so in summary, I mean, if we just look, NAND impairments widen the voltage distributions and increase the number of read errors. A different way to look at the same thing is after program array cycle, we have a certain number of kind of errors. Of course, it's not fixed, but a distribution of errors. And then as time goes on, the retention gets worse. These are not perfectly to scale. And the read disturb errors, as time goes on, you read neighboring cells. And as we go to more program array cycles, this kind of grows. We see the baseline goes up a little bit. The slopes here change a little bit with time. This is just kind of a different way to kind of show the previous graphs. So NAND flash, it's typically most you have about 4 kilobyte code words. It's about 16 kilobytes per page, which is one level, so the upper page, middle page, or lower page, and about 2,000 spare bytes. I know, for example, QLC, you have more spare bytes. That's because the quality is worse. We divided, as I said, 4 allocation units, 4 kilobytes each, and then different users may want to have different amount of metadata, and may want to put some CRC on the data to make sure that it's actually what they read back is correct. That's more 30, 40 bytes, but sometimes up to 100 bytes. And the remaining you can use for error correction parity. And I think everybody trying to maximize that. Forgiven. In the early days, BCH codes were used. Great. I mean, really fast and very predictable error correction. I mean, either you correct it or not. If you have too many errors, you fail. Soft decision decoding, unless you today or yesterday came up with some real breakthroughs, but it's not that simple. So now I think most drives are using LDPC codes, of course, very strong error correction capability. And soft decoding is relatively simple, although LDPC code itself is a little bit more complex. You see on the left side of this graph, that's when we do one read, so basically a hard decision, and we decode. And we see on the x-axis, we have number of bit errors that are injected. So let's say we inject 250 bit errors. Yeah, we can correct this, no problem, for this particular code in this particular situation. But as we go up to about 300, well, with a fairly high probability, I mean, 10 to minus 6, we actually see bit errors. And it's actually uncorrectable bit error rate. So you should really multiply this by 32,000 to get sector failure rate. What do we see as we do 3 reads? So we have 2 soft bits. We bring us significantly, we can up to almost 500 errors before we start to have bad. And with 7 reads, we can go even 550 errors. 9 reads, 11. You can do however many you want, but there are diminishing returns. And note, every read takes time.
So one quick question about that. Some places I've heard of do like even a low complexity decode the first time. So even if you read once, maybe you don't run your full min-sum decoder or something like that. Is that pretty common, or is it too much trouble to save the power?
The usage is of kind of bit flipping, basically bit flipping decoder.
Pretty standard, you think?
I don't know really, but I mean they're trade-offs because you need one more decoder, and if you then fail, you actually have a longer latency than if you just went with the min-sum right away. So, but that's definitely something that can be done, and you need to optimize. It's really optimizing the whole system. This comes down to, and but it's true. I mean, obviously, a bit flipping decoder can be pretty quick compared to a min-sum. Obviously, when you go to 3 reads.
So in the previous slide where it says 4 KB allocation unit, so it's 4096 times 8 is the message size in bits for the LDPC code, or is that the
If you use a 4K code, that would be. You could also use, for example, BCH. I don't think they used many 32K BCH codes.
Too long.
That's a little too long. So that's a little bit of a choice. I mean, we have experimented with different sizes because sometimes there's also been, 500K is also another allocation unit. No, 500, half a K, 500 bytes is another allocation unit. So, yeah.
Quick question. LDPC code, is it binary or non-binary?
Yes. Yeah, it can be both, and I'll show you a case where it's definitely can be non-binary. And there may not be too much gain from non-binary for some of the usages here, but I think you had.
When you add more reads, you also need to refine the distribution. Isn't that the cost also?
Well,
Translate the position to a probability. Right?
yes. So, of course, the distribution is what it is. You're not changing the distribution when you read, but you may want to sense the distribution to figure out basically what the LLRs are going to be.
It's not the cost.
Well, yeah, there is a cost. I mean, we even have a proposal where you actually sweep every single level to find the distribution to really optimize everything, and that's a huge cost. And I don't think any customer ever implemented that feature. It's just delay is too big. Sir, did you have a question?
Yeah, maybe I didn't understand it possible, but this is for TLC flash, right? Or is this for single level?
Actually, this doesn't matter because this is basically flip bit channel. We just, no, there's any NAND. This is single bit, the channel. Yeah. And here I can say the code is single bit binary LDPC. Okay, so then, yeah, in reality, you do need to optimize. So if you kind of go back here, I mean, you kind of need to know where you are, and I think I'll try to get back to that in one point later. So, yeah, I could have gone to the next slide because I have distribution here. So, when we fail, it's typically you do, some kind of retry, because obviously you don't want to give up right away. And we have the hard and soft retry. And as I talked about, insinuated that the optimal thresholds change. So if we look at this kind of retention plot, we have blue as optimal after 1 day retention. The dashed black line is optimized after a year retention. But of course, we don't always know exactly how long the retention is. Well, we can know some of that, but we also don't want to keep everything in memory. But So the optimal thresholds change. So when you do hard retry, all the NAND vendors, they provide read retry tables. And I'll show an example here in the next slide. And how we do. And then with soft retry, I think I mentioned, you 3 reads, you get 2 bits, 5 reads, 2.6 bits or so, 7 reads, 3 bits, and I guess you can do log 2 by yourself. So let's take a look at the read retry table. And it really is, okay, I think most of them are more than 16 entries, but there's no point having smaller font just to do 32 or 64 or something. But first entry, basically you see here for the upper bit, you move the A level by minus 33.5. This is some unit. We just normalized it to make sure we don't share any information we shouldn't share. And the E level you move by 5.7 units in the other direction. I'll show you this in the next slide. And then for the different middle bit, you actually have 3 levels you need to sense. For this particular coding that's being used. So when you do retry, you go in and you just pick this. So let's see. For the upper bit, A level, right here. So move that 33.5. And the E level, we move that 5.7 the other direction for this particular retry table. And this actually becomes very important because why not just do soft decoding? Well, if your level is not optimized, and maybe go back here, if you're at the completely wrong level, doing soft read is not really going to help you much because you're still going to have the soft information is not going to provide you more. You're still going to be error, all of them. So let's just see the read retry flow. We do the default read. Obviously, if that passes, we're done when we go on with next. If that fails, we set the read retry. And this is just an example. I mean, you can dream up a lot of schemes here, what you can do. But you set, okay, use the first entry in the table. And then you read and decode with this kth retry entry. If it succeeds, you're done. Go on with the next. If you fail, go on, you check. Do I still have retries left? Yes, I do. Increment K and continue. And eventually, well, you succeed. But if you fail, you go in to do soft 3 reads. But important here is when you do the soft 3 reads that you actually try to figure out what is the best kind of base threshold. You shouldn't just take any threshold. You find out which one is the best threshold. That can be a little tricky to do because you don't know necessarily, but you can look at things like, I mean, number of 1s versus 0s. You can look at syndrome weights. There are a lot of things you can look at. Obviously, if soft 3 reads succeeds, you're done. Otherwise, 5 or 7. If you want to go further, you can do that too. But here I ran out of space on the paper. So we go to RAID decoding. And RAID is, of course, a misnomer here. It's RAID as random array of independent disks. Stems from probably, I don't know, 7 disks on hard disk drives. But you have multiple drives. If one fails, you can basically XOR the information or use, I mean, that's kind of the simple RAID schemes. You can have more parity drives. But anyway, here we just do kind of RAND-like protection. So we have different dies. So an SSD consists of multiple dies with NAND flash on them. And what we're doing is that we're kind of XOR across all these. And if you note, this is a little bit close to the track ECC I showed for the HDD. So it's very similar. And obviously, if one die fails, it may be a bad soldering or something, you can just read all the other ones and XOR, and you have the data.
Quick question about the last slide. You do all the reads, you still have to map them to LORs, and the mapping to LORs seems like another place that you could try, you could have a table of mappings as well. Is it always clear what LOR you should get given some read pattern?
LLRs can be optimized. Yeah, it's
Would you ever rerun the decoder with two different LLR mappings without actually rereading the
You-
flash?
that is yeah, you can do that exactly, where you can see by looking at the data. I mean, you look at how many hard ones do I have, how many hard zeros do I have, and you can see, yeah, we probably want to optimize it this way. And like you say, no, this one failed, let's just retry again, because that retry, just changing the LRs, is very fast. There is no 50 microseconds reread. Well, if you do 3 reads, there's no 150 microsecond reread. It's instant, well, more or less. So, and okay, so this now, actually, how are we doing here on time here? Oh,
Yep.
yeah, I have. So this kind of comes a little bit to binary, non-binary, but I mean, if we look at TLC, it's really PAM8. So why do we only read 1 bit at a time? Well, one big reason is that reading 1 bit at a time is much faster than reading all 3. So if you want throughput, I mean, unless you know that you want to read all the data, but sometimes you only want to read one page. So it's a complete throughput gain. And but we always have 3 bits of information. So can we improve performance by reading all 3 bits? Yes, you can. And if you, for example, know when you're going to read the upper bit, you know that the middle bit and lower bit, if you happen to know that they are both 0, well, you know you're going to stay P3 or P6. I think you can be pretty certain when you then look at the threshold for this upper bit here. If it tells you that you're on this side, you can be pretty sure that it's here. The likelihood you make a mistake is very small. So that kind of, well, a very quick demonstration that yes, it can be helpful. And here, maybe the biggest bit of theory I have on the whole presentation, but operating word line improves the performance. If you look at the upper bit, and we look at, well, we have SNR on the x-axis, and we look at the mutual information for the upper page channel. And then when we do word line level, where we do the whole upper and lower bit channel, but still binary, we get significantly better mutual information. And then if we do on the non-binary channel, this improves even further. So there's clearly a gain here. And here I promised a little bit on trellis coded modulation. And I mean, this is really a conceptual diagram. This was big. I mean, 15 years ago, there's a lot of companies looking at trellis coded modulation because that was so obvious to do this for NAND until you got to try to sell the product to people actually building drives who wanted throughput. That was quickly killed. But there's still some interest because when we go to PLC, and if we really want to compete with hard disk drives, with orders of magnitude slower read, this actually may be very interesting. But okay, we use convolutional encoder, RAID 3/4, and these bits basically are the coset labels, and in this case, they're just uncoded. But you can, of course, you can do non-binary LDPC codes and forget about the set partition and cosets altogether. So basically block-coded type modulation. And we see, I said in each TCM symbol, 3 out of the 23 user bits are encoded by the convolutional code. And this is multidimensional, so we have, 3 bits per cell, and then we take 8 cells to encode a total of 24, or write a total of 24 encoded bits. And I just to kind of show the coset partitioning here, to simplify it, we go down to one dimension. So we look on the right-hand side, we have the 1 × 8 PAM, and a 1-bit coset label, the lower bit here, the red, it's 1 on the right side and 0 on the left side. And we just see instead of the 8 bits, we have dim in between 2 levels. When we do the coset partition and the daemon basic for these uncoded bits doubles. So not too much. And I mean, of course, the decoder, in this case, you recover by the Viterbi decoder to find the right coset label, and then you do the nearest point within the coset for the other bits. And of course, the performance here is determined by both the Viterbi decoder and the intra-coset decoding. When the Viterbi fails, you're in trouble. But I want to kind of, just because of the interest for future, we may want to revisit this kind of modulation type coding for NAND. Okay, so we talked about NAND format is fixed. We have SSD, MLC, TLC, etc. We have a fixed number of bits. So we can't really squeeze in more bits. For HDD, we can always run the clock a little faster and squeeze more bits or squeeze tracks more. Here, we're fixed. And the NAND is built basically assuming that we read one page at a time and we use effectively today an LDPC code. Polar codes, we haven't really seen, and maybe that's coming from you guys, but we haven't seen that breaking through here. LDPC, like I said, it's dominant today. Hard read, soft read when it fails, and the different error sources: endurance, program array cycles, retention, after you write, how long is the data valid, and read disturb, the read neighboring tracks, and then a little bit on alternative coding schemes. So this was a very brief overview, although longer than my allotted time. And there are many interesting problems. And in particular, because we don't have to adhere to a standard per se. We can do what we want, and we don't need to tell even, well, our customers usually want to know, but it's kind of, you don't need to tell someone else what you're doing as long as you provide the data back. So thank you.
Thanks a lot, Mats. So, all right,
Really,
get your hands up early.
Yeah. Thanks for the nice talk. You mentioned 90% in the data center is HDD, the data stored on HDD. I remember there's something called magnetic tape. Is that still a thing?
Yeah, tape is really big, but it's not necessarily, well, in the data center per se. That's how you define it. But if you include tape, the number would go down.
Okay.
Yeah. Tape is more archival type storage.
I see. It's probably not reasonably high speed.
Yeah.
What about spatial coupling? Is it a possibility to use it in NAND?
Spatial couple codes. Yeah. That's definitely a possibility.
I'm really interested in what you were saying about possible trellis coding for PLC. Are you, just to clarify, are you saying that in that for PLC, you would then read all 5 bits, so all 32 levels, to then provide the data for your Viterbi decoding?
I view that as a possibility, that when once you do 32 reads, well, once you need to do PLC, you need to do, 5 bits, you need to do 5 reads per bit anyway. So your throughput is reduced already, compared to TLC.
Yeah.
And maybe you're trying to compete more with HDD. And then you can say, well, if we have 4 milliseconds, or if we have 500 microseconds, it's still an order of magnitude improvement.
So just to go in a little bit deeper, because this is really interesting to me. If you were, so you can do set partitioning and still have the coset code itself doesn't have to be a convolutional based code with a trellis. It could also be an LDPC code just as well, and you can get the set partitioning gain. And so I guess what I'm wondering is, what block length would you be thinking about, and how do you think about that decision about whether the cosec code would be a trellis-based code or a message passing code?
Good research problem. No, quite frankly, I have not been thinking too much about that.
Oh, okay.
I-
Just passing it out
Yeah,
there.
it's a little tossing it out to kind of make this is really what may be a future. I mean, it was just 15 years ago. The problem now, if you talk to people, no, that we looked at that, so they don't like that. It's old, but sometimes you may like LDPC. You need to look at it in a new light.
Well, I guess maybe we can talk more about that.
Can you say something how you handle the different bit error rates, say in TLC, between the three different pages? I see the number of threshold is 322, and is it less of an issue when you go to 4 bits and 5 bits? Like in 4 bits, do you do 4, 4, 4, 4, 3, and then it will be like 5, 5, 5, 5, and 6? So then it's less of an issue?
It would probably be less on this because obviously MLC, it's 1 and 2 levels. So of course, that is an issue. Really, we don't necessarily control it because our friends, the NAND manufacturers, they decide how the media is read. So we have seen cases where they changed from kind of I think 223 to something like 133 or something, and kind of why did they do that? And then promptly they changed back. So we don't really know why, and that's a little bit of a problem, is that we don't have the whole story, and they don't want to share the details.
I thought it was our problem that they don't share with us. I guess
Yeah. No, we're a little bit fortunate because we work with pretty much every NAND vendor, so we have the NAND, but we don't get all the secret sauce.
They don't necessarily do balanced gray code.
Not always, but
Maybe our last question will be from.
Wondering about HDDs, you mentioned 7,200 RPM, and you mentioned a certain geometry for the read and the write heads and so on. Is there any game still to play to optimize that to maximize density? To re-optimize the channels or engineer the physics?
yeah, so you can't really spin faster because the disk would disintegrate. I mean, the 15,000 RPM drives are 2.5 inch, and then you don't have enough storage. That's all SSD today. But 3.5 inch, you cannot spin much faster, but you can spin them slower. Of course, your access time changes, but you can actually increase the areal density because your write response is faster. So there is some talk about that. Okay.
Thank you.